Welcome to another exciting class on rectification. My name remains Engineer Felix Ezoke from ITF ISTC Ikeja. We shall be looking at rectification. We talked about rectification in our lesson 1, just a little bit. We mentioned that rectification is the process of converting alternating current to direct current. Since our electronic devices makes use of direct current, it is necessary that we convert the AC current to the direct current. In the previous lesson, in lesson 1, we saw the characteristics of alternating current, that an alternating current oscillates. It changes frequency over a period of time, whereas a direct current might have changes in magnitude with time, but it is always unidirectional. Now, to convert alternating current to direct current, we will be making use of rectifier diodes. Rectification. We are going to be making use of diodes. This is the symbol, electronic symbol for diodes. So we can call this the rectifier diode. And this is the cathode, and this is the what? Anode. The cathode means negative, and the anode means positive. When you get the diode looks this way. It has a silver lining here, call it the banded end. So the banded end here signifies the cathode, and here signifies what? The anode. So this is the physical representation of a diode. So when you are looking out for the connection, make sure that the silver end, the tip close to the silver end is the negative, and the other end is the positive. What is the primary function of a diode? It is to allow current to flow only in one direction. That is forward bias. You can only forward bias means rather the flow of current in one direction and not the other way. So this is called forward bias, and this is what? The reverse bias. So we will have the diode in this way. So, however, there is a diode called the Zener diode that allows current to flow either in the forward direction or in the reverse direction. We'll be talking about that diode much more later. To achieve this rectification purpose, we will be using the characteristics of this diode, its ability to allow current to flow in one direction. So we are going to be looking at the characteristics of this diode, that is, its ability to allow current to flow in one direction to achieve this rectification purpose. Okay? However, there is also an IC called a rectifier that can do this. So there is a way we can arrange these diodes to help us to actually carry out this. And that process is called rectification. Now, there are different types of rectification. Types of rectification. A rectification could be either half-wave, a half-wave rectification, or a full-wave rectification. These are different methods. And we can also have the full wave, the popular one, bridge rectification. Now, how do we use this? The number of diodes that is required for this is one diode For a full wave rectification, it makes use of 2 diodes. And for a full wave bridge rectifier or rectification, it makes use of what? 4 diodes. What is a half-wave rectification? A half-wave rectification is defined as a type of rectifier that allows 1/2 cycle of an AC voltage waveform to pass while blocking the other half cycle or chopping off the other half cycle. In our previous lesson, we saw the waveform of an alternating current. So this is known as the positive half. This is known as the negative half. This is known as the positive, negative, positive, and so on and so forth. So this is called a positive half cycle, a negative half cycle, and then a cut in that manner, okay? Where this is what? The amplitude, A, okay? And from here to here, a full is called the time period of the wave. This is a full AC. Now, this is what comes to our what? Our sockets, our mains. In this part of the world, 220 volts. We find it in main, but our electronic appliances and some electronic devices make use of this amount of voltage? No. So there is even in your computers, laptops, phones, which are all electronic appliances, there must be a way we have to step down these 220 volts to a usable DC voltage that will be enough for our purpose and also not to damage our electronics components or to influence our active components, to either amplify or to switch or to do whatever purpose which we are building that electronic circuit for. Now we are going to be looking at the circuit diagram. How do we construct the half-wave rectification? We have said that the half-wave rectification makes use of 1 diode. So we have a voltage source, which can be what? A transformer. So this is the way we draw it. So this is the single diode, okay? And then we'll have the load. And then we'll have our load. So this is an example of a half-wave rectification where it makes use of 1 diode. Now, during this process, where we have the alternating current flowing through it, since the diode allows current to flow in only one direction, the wave output of this will look in this form. During the positive half cycle, which the diode will become forward biased, meaning it will conduct electricity, it means that during this positive half cycle, D1 will conduct. During the negative half cycle, that is when it will be reverse biased, when we have the negative coming here, okay, because it changes positive to negative to positive to negative. So when it's positive, it flows. When it is negative, it will not flow. So nothing will happen here. During the positive half cycle, we have another conduction. During the negative half cycle, nothing happens. We have what? Another conduction. So this is how the waveform from a half-wave rectifier will look like. So we have series of gaps in this way. Okay? So, but like we mentioned in the last class, we said that other forms, once it's unidirectional, that we have achieved a what? A DC output. So this on its own is a DC output. So we have succeeded in changing this alternating current to what? To a direct current. However, there is a disadvantage to this. Disadvantage is that the output is difficult to filter. The output voltage can also diminish considerably when the power supply is connected to load. Also, it can put a disproportionate strain on the power transformers and on the diode. However, the advantage could be in terms of cost. Since we said it's only one diode, in terms of cost, one can say, well, it costs less. Again, it is useful in power supplies that need not deliver much current or that do not have to be specially well regulated. Okay? So these are the areas where you can use a half wave. If we don't require much regulation, that is an unregulated load, fine, the half wave rectification can do the job. So this will take us to the full wave rectification. The full wave rectification converts both polarities of the input waveform to pulsating DC, that is the direct current, and yields a higher average output voltage. So in this case, let me just draw a transformer, okay, as another voltage source. So we have a step-down transformer. Okay, let's say this is 220 volts. Okay, so we could have something like, say, 12 volts. 12 volts or 13 volts, whatever it is. But still AC because it has still alternating. Then we can place our diodes here, our two diodes, in order to achieve a full wave rectification, RL. So we call this D1, we call this one D2. That is the two diodes. Okay? So these two diodes will help in taking care of the disadvantage in the half-wave rectification. The full-wave bridge rectifier is even a more better application of the full-wave rectifier. All right? We will use the full-wave bridge rectification to further explain the advantage of having the full-wave rectification, because these diodes will be arranged in a bridge format. Okay? Now, and then we'll look at the advantage of the full wave and the disadvantage or advantage of the what? Full wave bridge rectification. I will leave you to look for the advantage, or read up the advantage rather, on the full wave bridge rectification. The full wave rectification is just like the opposite of the half wave rectification. That is, the output will be easier to filter. That's an advantage when compared to the half wave rectifier. The full wave rectifier is easier on the transformer and the diode when compared to what? To the half wave rectifier. And then when the load is applied to the output of the full wave circuit, the voltage will drop less than is the case with the half wave rectifier. However, the disadvantage could be on the cost, since we are going to use more diodes compared to the half wave rectification. So let us explain how this advantage or much smoother DC output will be achieved using the full wave bridge rectifier that makes use of 4 diodes. Okay? So we are going to be drawing that. We have it in a bridge form. All right, so this is the way we are going to connect this output. Okay, so this is the output, this is the positive output, and this is the negative output. So this is the bridge rectification. Two diodes facing a particular direction, another two diodes facing another direction. So we can label this D1, D2, D3, and what? D4. These are the four diodes that are used in full wave bridge rectifier or rectification. Now, how does this work? And then we'll have, okay, let's have our load, RL. To explain this, we are going to look at the alternating current coming from the transformer. Okay? So we have our transformer, which is oscillating, the oscillating transformer, or rather the oscillating AC, comes through from the transformer stage, and then we'll go into the rectification stage. So this is known as the rectification stage. So the rectification will be done at this stage. So we have the transformer stage. The 220 has been stepped down, but still contained is an AC voltage. Now, the current will flow in this manner. The current will flow in this manner. When we have, during the first cycle, first positive cycle, negative, positive, negative, positive, negative. During the positive half cycle, remember, this is the way, this is cathode and this is the anode. So the current will flow in this manner. I will represent it with the green color. The current during the positive half cycle, this is the flow, the direction of flow. The current will flow through this way. When the current wants to flow into D4, it will not go through D4 because it will be reverse biased. So because we have the positive going in at the positive half cycle. So it flows from positive to negative, and then it flows through the load, goes through this way, this is the path, and then comes through this way, and then goes through this way, okay? And then flows back to the transformer, and then the cycle repeats itself. You can see the direction of the positive half cycle flows through this. So D1 and D3 conducts. The conduction D1 and D3 conducts. Now, the resultant waveform will be this. Okay, let us have all the waveforms on the right-hand side of the board. We have this alternating current, that is the AC, input voltage. Now, from the output from D1 and D3, we'll take this form, okay? This is the positive half cycle they conduct. During the negative half cycle, D1 and D3 will not conduct. So, you can see this one will conduct, this path will conduct, and so on and so forth, just like that. This is the output waveform from D1 and D3. Now we'll go to the output waveform for the remaining one, D2 and D4. So during the negative half cycle, this will not conduct because this would have been also reverse bias. So this is the cathode. The negative will flow in this manner, flows this way through D4, okay? I'm using the black marker for that. It flows through this way, okay? Come down this way, because if it attempts to go in through here, this will also be what? Reversed bias. So it goes this way, follow the black marker, goes through the load, okay? And also flows through D4, okay? At this point, it goes through here, D4, negative, and then come back to the load. So this is how it's going to flow. So the green marker is representing the positive half cycle, and the black marker is representing the negative half cycle. So we can see what is happening now. During the negative half cycle, D1 and D3 will block, that is, will not conduct. But D2 and D4 will conduct. So we are making good use of the diodes. So this is the output waveform. When this will not conduct, this will what? This will conduct. Okay? This will not conduct. At this point, this will conduct. At this point, this will what? Conduct. Will conduct. Now, putting this together, putting D1, the output waveform of D1 and D3, plus the output waveform of D2 and D4, will give us a continual supply of current to the load. Can you see that? Can you see that? So for every gap which we noticed in the half wave rectifier, it has been compensated for in the full wave bridge rectifier. That is, you can add this and this together. You can see now we have a continuous pulsating DC. That is how we make use of the efficient use of the transformer. Look at your screen right now and see the resultant waveform of the full wave rectifier. You can see that we don't have any gaps anymore from the screen. You can see the output that is constant. Though it contains ripple, but then our output is consistent, meaning that we have achieved in converting the alternating current to a direct current, though with ripples. So this is how the full wave rectifier achieves the process of rectification. That is, converting alternating current to what? To a direct current. And from there, it goes on to the load. In our next class, we'll be looking at filters and regulation. That is, if this signal, that is the direct current, is it enough for what we need? We need to do what? To improve on this in order to get a fine DC output, which is virtually what we need, a current that is unidirectional. So it is steady. We need a steady output, irrespective of time. It will be what? It will be steady. And that is what we are gunning for in our filter and the regulation stage and voltage regulation stage. So until we meet next time, we will end here. Remember your assignment. Look for the advantage and disadvantage, or read up the advantage and disadvantage of the full wave bridge rectifier and compare them with the half wave and the full wave rectification. See you next time. Have a great day. Thank you.